endless flight, chasing stars and chasing light. Black holes hide where we can't see, secrets they will always be. Yet we dream relentlessly in the space where souls roam free. Universe so wide, so vast, moments giving never last, floating through the starry past, journey far, we're going fast.
And look out. Hey everybody, it's Mark. How are you doing? Daryl is again unable to join us tonight because his computer is giving him problems. He had some choice words about Microsoft. That's all I'm going to say. But I actually showed him a picture of a mini computer that he can get that we use. It's this big and literally the size of a slice of bread, a little thicker. And it's a beautiful little computer that will serve all the needs that he needs. Unless he's a real high-end gamer, which I don't think he is, this will just do wonders. Marianne, who's obviously part of our Happy Triumvirate and SkyTour live streams nonprofit, she has one that I had. I instructed her to purchase, and then I helped her set it up. So it was actually quite good. Quite good. Today, I had a 2-hour lecture to deliver on a quantum mechanical concept that talks about interdimensional travel, something Avi Loeb at Harvard's talked about, something I've been talking about for many years. And it looks like modern physics is coming on board with it. So it's something really interesting. And as I told you before, it's the way in which they get here from far, far away. It's literally the only way they can get here, in my view. And I think it's just, unfortunately, it's out of our reach right now. So it looks like science fiction to us, and so people sort of dismiss it. However, we shouldn't be so dismissive of this probability. I mean, if you want to know what the lecture was, it's actually on SkyTour livestream channel. You go back and look, and it's called Yes, They Are Here, the way that UFOs actually most likely operate. And it goes through the interdimensional travel concept, how it works, and you can stop it, rewind, and look at it again if you have to. So that's pretty cool. I think that that's pretty cool. Evan, SkyTour Life fan, says, "Oh no, I think the aliens have taken over Mark's body." No, not at all. No, I will not admit it, Evan. I will not admit it. I am fine. It is you that is in trouble. Just kidding. So anyway, as you can see, yes, we have the moon here. Okay, the moon is going to be in our way now for a while to go. But I will tell you this. The next telescope that we're installing, we're going to have it installed in February, hopefully in this new site. Again, anything you can do to help us, let me tell you, if you can go to skytourlive.org, okay, there, or go here and click the donate button, or just join our Patreon. It doesn't matter, $2, $1, $3 a month, whatever it can be, or a single donation. We need to be able to pay for this spot because it's a prime spot on top of a mountain with professional astronomers, and the cost is not out of this world. In fact, it's literally half the cost of what it might ordinarily cost because we are a non-profit doing outreach astronomy. It'd be a shame if we couldn't get it, but I'm hopeful that we'll get some people to help us. But otherwise, you know what? Enjoy it for free because it's fine with me. I just would like to be able to have it at least cover its own expenses, because right now it's exceedingly close and not easy. Anyway, I'm not going to turn this into an NPR begathon. I will just say that if you can help us, great. And I'll mention it one more time later on. This will stay atop here so you can see that if you have an idea that you might want to help. So anyway, the moon's first quarter tonight, as you see. And as I said, Daryl won't be joining us because his computer is literally twisting him in a knot. And if he gets another little mini computer, I'll help him set it up if he doesn't know how. I think he does. And then we'll go from there. But he won't be long. He'll probably be able to join us perhaps Monday. I'm not sure. So that said, we're going to go off and running and look at a few things. So one of the things we're going to look at tonight is a supernova remnant. We looked at the supernova remnant called the Veil the other night, and what we're going to do is look at the central veil, the central part of that, and a special feature of that tonight. And then we're going to look at a Wolf-Rayet star. That is a star that is hot and young, and is so hot and so young, among the hottest stars around. It's actually pushing its outer atmosphere outside the core of the star, which is about 20% of the size of the star, pushing that whole outer atmosphere away from itself. Okay, it's a star that's literally committing suicide right in front of us, and it will ultimately end with a major cataclysmic explosion called a supernova. Yep, Genghis is here. Hey, yes, look. First, I want to say hi to everybody. I know that I'll make it quick. Wayne Pinkham, friend of mine, who lives in a nearby. I think it's Simsbury. Wayne, right? And he's joined us tonight. He was first. Waldo is with us. Waldo Hiding. SkyTour fan is Evan. He's here. Michael Galea is with us, who's also watching the college football game. At the same time. And Sam S is with us. Hi, Sam. Nice to see you. And Alicia is here. She's doing some coding while she's watching, which is kind of cool. And Carl Becker has joined us tonight, along with Old School and Richard McFarland, who I talked to Richard today on the phone for quite a while. He's actually a really cool person, and he won the binoculars last time, and so it was really nice to talk to him. And he's overjoyed. He'll have a good time with him, And as we move forward, remember, we still give away telescopes, and we are looking forward to giving away a night vision system. And when I'm at Contact in the Desert this year, we may be giving away a night vision system there. Okay, so hopefully if you can go to Contact in the Desert, you can join me for one of my several lectures I'll be giving. I might even be doing another one of these, another live sky tour there, which went very well last time. And so we'll have some fun. I also want to say hello to Donald Kunzer and Mr. Django. That's Steven out in Belgium. A great guy. He has a great astronomy site. You should check out Django's Backyard. It's really cool. Okay. And then, of course, Victor Anthony is with us. Hi, Victor. Nice to see you. And another face we haven't seen is Rayola Resner. Hi, Rayola. How are you? She's in northwestern Ohio. And she appreciates the stream. Thank you. That's very kind. C&D Boy, our Canadian buddy, always here. Dave C. was in the lecture today. He knows all about it. And I think he had a good time based on the many questions he had. It was funny because Dave was sitting out there. And I met Dave just once before, a long time ago. And today was another time I spent several hours with a full house. I mean, the restaurant was filled, with on this side of the whole restaurant. It's like a banquet type side. And every chair was full, except maybe a couple. And it was very, very cool. There were some in the back that weren't covered, but a lot of people there. And Dave had a MUFON hat on, a Mutual UFO Network hat, because it was a MUFON meeting for Connecticut. And Dave was actually coming up with when I would ask questions of the audience, Dave would respond. And he would not just respond with a bland answer. He was exactly right. So I wanted to just give him a shout out because he's a really smart guy. So I kept saying to the director of MUFON for Connecticut, I said to Mike, his name's Mike Panicello, I said, Mike, you got to give him more than just a hat, man. He's getting these answers right. He's absolutely, totally cool here. So it was kind of funny. It was sort of a running joke as the day went on there. But it was really cool, and Dave, I think, had a good time. And I'm pretty sure that we'll do more of those. I speak a lot of places in Connecticut. I also speak around the country and the world. So I like to spend time here in my stomping grounds too. It's really nice. So yeah, SMA Sky's with us. How you doing, man? Good to see you. And Science Bob. There's Bob McGuire. I talked about you today, Bob. I did, because I was talking about the USO sighting I had on the submarine, and I brought up yours on the USS Hampton submarine. That's pretty cool. Also, Bob, I think you know this, and I might have mentioned it to you in a message. I was told I might be asked to testify at the U.S. Congress for the hearings on UAP, and if I do, I want you to know I also gave your name to them too, as another witness to an event under the water, and I think that's pretty cool. So hopefully you can do it. Hopefully they'll ask us both to do it, and that'll be kind of cool to meet you in person in the hallowed chambers of the Congress, but you don't count on anything until I'm there, right? So anyway, it's good to see everybody, and I want to see, Richard Spencer's here. I've missed you before. Sorry about that, Richard. And I think that's everybody. Yeah. Anyway, so we're looking at the moon right now, and what we're going to do, I just have this up because I want you to see something cool when you came in. All right. Now, with the new telescope that's going in Benson, if we can get the funds to actually do the install, and hopefully some of you can help us with that, as I said, we're going to be able to dive right into these craters. And when the moon's out, we'll no longer be crippled. We'll be able to look at craters like this crater and just zoom in and check out huge, wonderful details in there. And that's going to open up a whole new world of astronomy education that I can do for you. Because I have a huge, I've done lunar programs for decades, and I'll be able to do a whole lunar program on everything we're seeing here, look at some of the really cool features on the moon, teach you all about them, and we'll have the whole night to do them because the moon will be out, and when it gets to like gibbous, waxing gibbous, where it gets to about 3/4 full, that's about the last logical time when we can do the moon. When it's a crescent, when it's first quarter, when it's waxing gibbous, all those days we can do it because the moon will have plenty of detail on it and plenty of detail. But when you go to full moon, well, now the light is striking the moon from behind us, hitting the moon, and so we don't see any of these shadows like we see now. There's no terminator. It's around the other side of the moon on both sides, so we don't get to see that. So that said, we will probably do as we have before. We'll just look at the moon up until just before full, and then we'll just wait it out until it goes to the other side, and then we'll be able to look through the astronomical stuff again with both telescopes. Also, because the new telescope is going to be 200 miles away from the current telescope, we're going to try something never before done, and that's a 3D image of the moon. We'll take a picture with this telescope. We'll take a picture with the other one at the same exact time, and you'll see them both on the screen, and we'll take the pictures. And then we'll assemble them into an image that will be a 3D image. So one on one side, one on the other, and you do that cross-eyed thing, and you'll be able to see the moon that looks kind of bulbous. It'll look like it's 3D. 200 miles should be enough to actually get some 3D out of this. Okay? I mean, people have done it with Jupiter, for crying out loud, so I have a feeling we'll be able to do it with the moon. So that'll be kind of cool. Anyway, let's go to our amazing planetarium program. And I've already pre-selected this guy right here, and we're going to look at it first because it's going to be the first one to set. This is called the Crescent Nebula. It's actually the most amazing location in the sky in this current time of year for looking at the things we call Wolf-Rayet stars. A Wolf-Rayet star is a star that has I'm going to shut this back to a second here. 1 second. Okay, you'll see stars in just a second. Okay, now we should see the stars pop in. There we go. All right, and I'm going to back out because we're at 54% here, and we'll fit the width. And let me do an identification, see if it's in our field. If it isn't, it's only because I haven't really got the telescope fully aligned yet. Okay, we got the Hipparchus star. Okay, that's cool. So we can center that in the view. Yep. And that'll get us, once we center it in the view, we'll be fine. So that'll come over here in the center. And you'll see that it's going to be in our crosshairs. Okay, right there. And there it is. So that star then is the one we're going to use to align the entire telescope on. That's Hipparchus 99893. So what we do is we come in here, we zoom in. It's going to be really close anyway. All right. And we're going to set up our field. All right. And now let's go and we'll do a search on the star Hipparchus HIP. That's the name of a star catalog. And I think it was 99893. Okay, cool. So 99893, Hipparchus 99893. There it is. So let's go to that. And it's over there. Yep. Okay. So we're gonna now just say, all right, align. So that we're gonna take our crosshair and it's gonna line up on that. So now, when I go here, it's going to be dead center in the view. It's like a little alignment process I do. It's kind of a cheat, but I like it. Right? So we'll set this up again, and it redoes it. So now we can go over to our planetarium and say, hey, Crescent Nebula, guess what I want? I want you to come into the view. So I'm telling the telescope to go there. As we do, you'll see the stars move, and you'll see the Crescent Nebula come into the view. Okay. And there it is. You can see it right there in the center as promised. Okay, so what's happening is there's a star in here, this one right here. And this star is extremely bright. It's very, very hot. It's very, very young. And its stellar winds are blowing, as I said, that entire outer layer of the star off. Now, you have to understand the architecture of a star. We have the core. And the core is approximately 15 to 20% of the overall size of the star. Okay, with a small star that tends to be a large amount, but with a larger star, when we have a red supergiant, that core is disproportionate to the size of the star. It's the size of the star when it's normal. Okay, but when it really bloats up, then that core is a little much more tiny. So that guy right there, right, that bright star right there, that's the core of this star left behind, but the core is still fusing very, very violently higher numbered elements in the periodic table. So that means that what we're looking at is we're looking at a star that's really literally got only its core left, and that rest of that envelope around the star that makes up the big sphere that we're typically expecting to see, that's all the stuff, just like any other star that's in the star that it was made with, and it's just along for the ride. It doesn't do any fusion. There's no fusion happening in there. It's all happening in that core, where fusion occurs in that core. Outside that, it's just plasma. It's atoms without their electrons. It's just protons and free electrons running around in a tremendously violent environment. So let's go to 25 seconds here. Let's go here, and let's do a 25-second photo. Okay, and 25 seconds, I can say 25,000 for milliseconds, or I can say 25s. And then we'll go to our low light mode. I probably should focus this before I do that. So let me, now that I just lied to you, I'm going to break out of this for a second and do the focus routine. You can see it there because the focus is not perfect yet, and I'm going to just get that, and you'll get to see the focus routine, which is really cool. All right, so the stars are a little bloated now because they're slightly out of focus. So I'm going to bring up our focusing tool, and we're going to focus down, and it's going to make a parabolic curve, and then it's going to solve for the bottom of the parabolic curve, the intercept on the axis, and that intercept down there at the bottom is the best focus position. So right now we have 61 stars, and now 52, all right, and 47. So clearly the focus is coming back out, and now it's 108. It's getting better, all right, and then 104 right there. You can see the number right there. Hey Genghis, Daisy and Zoe, how are you? Yeah, They Might Be Giants. That's a great band. That was a Genghis comment. The sun is a massive incandescent gas. They might be giants. Okay. The guy that's in here from time to time, his name, he calls himself Water Rat. That's Matt, and he's a big fan of They Might Be Giants, and sometimes he's playing them when he's here and doing work. Hey Mort, how you doing? Mort the Orc Cloud. So now you see our curve here, and in a moment you'll see a line that comes in right about here. And that's going to be where the focal point is, okay? So right about now I'm expecting to see a line show up here. There it is. Oh wow, right where I was. Okay, so at this point, if I wait just a little bit longer, what will happen is it'll automatically say, okay, that's the best focus, and it'll just start to refocus. So I'll just wait for a second, and you'll see that line start to move across as it moves. There it goes. Moves all the way to the out of focus position, and then to the total in focus position. Now, why does it do that? It racks it all the way out and then all the way in, so it doesn't have any loose focus adjustment. So you have to get it all the way back out and bring it back in. That stops like a backlash in the focus, because the knob has some play, if you think of it that way. So here now we are totally focused, and I can get out of this. It's done its job, and we'll come out, and let me just drop this a bit, one notch. Okay, so there we go. And now we're gonna go back to a 25-second shot here, and I'll do 25,000 this time. Doesn't matter. Not 250,000. That'd be 250 seconds. Okay. So here we go. And now we're gonna come out of our low light mode here, kind of like our finder mode, and we're gonna go into our live stacking mode, which is our deep sky mode. Yeah. Hey, Native NC, how are you doing? I'm assuming that means North Carolina, right? Yep. Yep. Why does the sun shine by They Might Be Giants? Thanks, Genghis. That's cool. Mort has PC problems. Oh, I'll see that blue. Okay, that blue is because we have a first quarter moon. So you might say, oh no, that light pollution is going to ruin our night. And it will when the moon gets brighter. But right now, we're going to process this and get rid of that blue color. Right now, I'm going to do a color correction. Now watch what happens. Right now, it's looking better. And if I just take our black level, climb the peak, the white peak you see there, just to the left, right? We see this. You see these other nebulae out here. This is a region that is just filled with other nebula. Many other nebula. Okay. Now let's, and this is actually, there we go. That's a little better. So now you can see, and I'll zoom out a little more, so you can see it in earnest. There is the Crescent Nebula. That's the star right there, and this is the outer layers of the star that have been blown off. The others are here, and we're actually somewhat close to the horizon. If you look here, you can see the telescope leaning way over to the west. Okay, that's west, that's east, and toward the back of the building, that's north, and south is right out the page toward us. Okay, so the best position for an object like this to view is when it's actually probably 45 degrees and higher in the sky in that little arc. That will deliver the best views. But when this happens, all we have to do is just spend a little more time, take more pictures, and they'll come out great. I'm going to do one right now. If I click this, you're going to see it get instantly better. Watch this. Ready? Hey, watch. Boom. How about that? Okay, that's an instant enhancement that I can do right there. Another one that I can do right now is play with the curve. I'm going to take this mid-level here. If I bring it in too far, you'll see that it gets really bright. But if I pull it down, you'll see that everything starts to look a little better, and color rendering is better too. And we can look at the negative of this, so you can see more detail in here. You can see how that looks. Okay, very, very cool. Hi, Judy M. Okay, this is the Crescent Nebula, as I said. So if we come in here, there's the Crescent Nebula, and I'm going to highlight that and say set the target name, and that goes up here, and that's what will appear on our server at skytourlive.org. Okay, right there. So what I'll do right now is save this image with annotation, and it's going to go to that directory on the server, and you'll see that image up there for those that want to get the images from tonight. And then we'll save it again. We've got a lot of images that didn't take, and I think we're just on the border. We got to bring this up a little more. Okay, so we may have some wind out there, which is responsible for these not coming in, but it'd be very mild. I've had this is the full width half maximum filter, so if we see green bars from now on, it'll mean that we are falling under the radar for the error level, which would cause our stars to be elongated. Yeah, there we go. So here's 3. Now if we zoom in, look at this beautiful object. You can see this detail in here. Okay, so there's the star that's lost its entire outer atmosphere right here, and this is its entire outer atmosphere. The star is so hot, so hot, we're talking 45,000 Kelvin degrees. If you go into Google and say 45,000 K in F, for Fahrenheit, or C for Celsius, you'll see what it is. And 45,000 Kelvin is kind of close to 45,000 Celsius. And then, so if you convert that to Fahrenheit, you'll notice that we're talking a huge temperature here, something about 60,000 degrees Fahrenheit, even more. So the star is very, very hot, and its final destiny will eventually be a supernova. It's going to go supernova, and that'll be cool if we can see that. And it's called the Wolf-Rayet star, and that's wolf, like the animal, and Rayet, R-A-Y-E-T, the names of 2 people that found it, Wolf and Rayet. And the 2 of them are responsible. Now, there's many different kinds of Wolf-Rayet stars, okay? And that's a whole talk in itself, which I give. But I want to caution you that we have to be very careful with these, because sometimes we don't know, we don't know which kind of Wolf-Rayet star it is until we look at the spectrum and see what kind of emission we're getting, either in the star itself, okay, because the star is surrounded by this layer of gas nearby, and they will give off these emission lines. These are emission lines. These are glowing gas lines here, and we'll see them. We'll see oxygen in here. We'll see hydrogen in here. We'll see neon. And the thing that's interesting is, in the universe, hydrogen is the most abundant. I've told you this. Helium is the next most abundant in the universe. 3rd most abundant is oxygen. And 4th most abundant is, believe it or not, carbon, right? What you're made of. So it stands to reason that carbon is responsible for a fundamental support of life, right? Not only that, the 5th most abundant element is odd. It's one that we can't use in our bodies in any way, and that's neon. Neon is the 5th most abundant element because it's easily made in stars, all right? And it's a noble gas, and so I think that's pretty cool. Judy M says, Mark, have you ever taken a picture of this one before? Yes, Judy, we've taken a picture of this, and once our application is up, you can actually do a search for all Crescent Nebula and get all the many, many shots of it we've ever taken. And that of course is courtesy. That's courtesy of Izabela Melamed from Bulgaria. Richard McFarland says, "Hi Mark, thanks for the chat today." Oh, you're welcome. It was good to talk to you today, Richard. Richard won the binoculars the last stream, if you remember, along with Karen Belmont. So we'll get your binoculars off to you, Richard, and I wanted to talk to him just to say hi and so forth. Alicia says, Darlene is here. She's wondering if you can give her a fix of a dwarf planet, or when you could. Okay, she wants to see an asteroid or a dwarf planet. Yeah, maybe. Let me go just check here. Let's go look here. See if we've got any. They're probably going to be near the celestial equator. So we're going to have to go down here. Well, they will be near the celestial equator. Alright, so let's do that. We're going to head toward the east right now. Okay, I'm getting a spam call from a nearby town. How about that? Okay. Alright, so if we come over here and we come over here, it's minus 15. Alright, and this is the celestial equator here. Right here. So somewhere in this line, we'll be able to see an indicator of an asteroid. If there's one in here, we'll see it. It'll show up with a label. And I don't see one. Let me try zooming out a little bit. Alright, yeah, I don't see one here. At the 0. Here's the moon. I'd have to look up and see if there's any out here right now. But we'll make an effort at showing you some of those, because I think they're really cool. We'll get to those. So right now, okay, the moon is in the southwest right here. And we're actually looking up here in the northwest. So the moon is not that far from what we're looking at right here. So the Crescent Nebula, look at the detail. We're getting this detail, and it's actually pretty good for having the moon out and for being low to the horizon. And by taking more images, as you can see, we're getting rid of a lot of that noise. So I'm now going to put another bit of sharpening in this. Watch the detail in here right now. You see this? You see how this is now sharper? Yeah, this is called an unsharp mask. And in astronomy, we use this very often. We create what's called a convolution matrix. So the adjacent pixels to every pixel determine what that pixel's value is going to be. And so by setting those values, we can shunt the data one way or another and make the image sharper. I wrote a program with my friend John that the Hubble team used initially to look at all of their imagery, and we wrote it just because we wanted to write a little program that would help. So the Space Telescope Institute actually used our program to look at the initial Hubble data, because we were able to make these convolution matrices very easily. And now it's all throughout Photoshop and PixInsight and all these other places. You know, we didn't create it and we didn't invent it. It's a mathematical thing, and it really is cool. You know? And Mort Ord says, not all asteroids are dwarf planets. Of course, that's true. Yep. That is true. Yep. Let's see how we're doing in terms of... Yeah, see, we have this set up now, so we're going to be getting all good values now. So we're working within our limits. Nice. Okay. Cosmic Flow is here. Hey, Cosmic, how you doing? Yeah, again, this is the Crescent Nebula, a Wolf Rayet star. I'm going to save this at 20. All right, and then move on to something else. JSCO 77's with us. Hey JSCO, what's going on? And we should have 20. There we are. We'll save it. All right. And then save exactly as seen. What does that mean? We save a ping file, a PNG file, out to skytourlive.org. If you want it, you can go to skytourlive.org, and probably by the time you go to where this is, it'll be there already. But this is right here. This is the image going up there right now. Let me bring that up. There it is. That's the image going up right now. That's up there, and it's going to be, all this detail is going to be yours for free, taking it. And believe it or not, we can process that even more and make this really sharp and beautiful and pretty. And we do that. And for the Patreon subscribers, we'll actually do that for the upper level Patreons. We have a whole suite of imagery we've done this to. And it takes us hours to do it. So clearly we're going to, it's something that's for like people that can pay. Epic TV. Hey, Anthony's with us. How you doing, Anthony? Good to see you, brother. Yeah, Anthony's cool. You got to check out Epic TV. He does some cool stuff up there. Yeah, very cool. I'm glad you're here, Anthony. So happy to see you. Yeah. Okay, so 23. We'll save this one more time. And save exactly as seen. And he says, Gutsy. Good to see you. Oh, yeah, happy holidays to you as well, Anthony. Very happy to have you. Okay, let's go check out. And Michael Hendricks with us. Hey, man, where you been? You're usually the first one, man. What happened? He's slacking. Let's all just get on his case. I'm kidding. He's cool. All right, we're going to go back to our. We're gonna get rid of this because we're done with this. And now we will go to our low light mode. All right. And move to the next object. We're going to move to the central veil now, which is very cool. All right. So the central veil is actually not very far away from this. If we go to this location, oops, the wrong location, sorry. If we go, let's go here. Back to the west, because we don't have much time to look at it. All right, there's Jupiter coming up over there. There's Aldebaran. All right, we got the 37 cluster coming up. That's gonna be pretty when we see it. Okay. All right, let's do this. Gemini is coming up. That's cool. All right. That's coming up in the northeast. Now let's go, and let me just do it this way because it's giving me trouble. No, the Crescent Nebula is not down there. What are you talking about? Excuse me. Oh. I think I screwed it up. Hold on. Okay. I actually accelerated the time by accident. Yeah, that's more like it. Excuse me, I'm going to take a little drink of water. I was speaking for a few hours today, so my voice is a little rough, but we're good. Okay. So let's now go over here, not far away, and we're going to go to a spot in the sky, and it's going to be right here. This is the central veil. This is the western veil. This is the eastern veil. And this is a supernova remnant expanding outward about 8,000 years ago. That's about 1500 to 1800 light years away. And so we'll go to the central veil region because this has got a lot of detail in here. So let's do that by doing this. And now the telescope will head over there. Here it goes. And let's let's fit the entire width in here. These bands are temporary. It's because of the way the data is being transmitted to us. If I do this, they go away right away. And if I do that, we get our better speed. Okay, let's see if we are close enough. Yeah, Pickering's triangle's right there. Okay, good. So do this. I'm gonna move us to the east a little bit. Okay, like this. All right. Okay. Now we'll go north a little bit to bring it down. We'll try this. We'll see how much of it this gives us. You have to see all this. This is just so detailed. So much stuff going on in here. Jessica S. How are you? Nice to see you. Okay. All right, we are getting our guide star. You can see that the numbers are flowing over here. That means we got a guide star. There goes a Starlink satellite. And people ask, how do you know it's Starlink? I know because the length of this is a 1 second exposure, and the speed at which it goes through the shot gives away that Starlink, and the angle it's on tells us that it's the Starlinks that are going at those diagonal angles to have overlapping coverage. Okay, this will be 25 seconds. Again, more spam. Get out of here. Okay, 25 seconds. There we go. All right, and we'll go into our live stack, and we should see Pickering's triangle right here. Yeah, we're going to get rid of that. That's our previous one. And the next image will be of this. I'm going to just take this just over a tiny bit so we can see those numbers here. Okay. All right, let's see what we get. Wow, okay, that's good. We have Pickering's triangle here, and we're at the top of Pickering's triangle, and I'm going to color correct. Okay. Oh yeah, you can see that now. Look at that detail. Now we're gonna push a little bit, and we're gonna show you more. Look at that. So up here, we have all this stuff up here. All right, and then down here, this is Pickering's triangle right here. We'll drop down in the next exposures, and we'll actually show you that too at the bottom, and then we'll put it together as a combined composite, which is really cool. All right, so the way to do this is we're going to come in here, and we're going to do this right here. We're going to say Pickering's triangle. Set the target name. Okay, and now that target name is up here, and that's what it'll appear on our server at skytourlive.org, where you can go check it out. I want to thank those that actually did some contributions to us from the last time we were streaming. That's very, very appreciative. I'm appreciative of that. I don't make any money on this. I'm not charging any money. I don't take any money for it because astronomy is my passion. As an astronomer, this is what I do, is to show you the things you can't see. And that's what this is. This is gorgeous. You're welcome, Genghis. Genghis says amazing. Thank you. So the other thing too is this is all in these filaments. Let me see if I can zoom in on the filaments now. I want to show you something in particular. As we zoom in, you see this? See that string of stars right there? Isn't that weird? Seems to be following a filament or part of a filament. Here's what could be happening. Okay, as we look at this, we see these filaments now. those filaments could be, as they push outward, they're compressing material along the way as they go. And this could have resulted in a string of star formation along the way. And maybe this string of stars is the result of this filament moving outward from the supernova center. Now, this one is the central veil. The ones on the end are moving outward as we can see them. But remember, this is three-dimensional. So this one's either coming toward us or going away from us, because it's the central part. So that's, I'm sure there was a Doppler study to show which way it's going, and it's probably a mix of the two. Now, as far as the color we're looking at, look at how beautiful this is. Wow. Okay, let me explain the colors. Because these colors, now I've given the color rendering on our system a shot in the arm, and we're actually getting the colors that are actually very much like they really are. Okay, so we're looking at these teal blues. This is doubly ionized oxygen in here. The red is hydrogen. Remember, hydrogen, the most abundant element in the universe, and oxygen, the third most abundant element in the universe. So it stands to reason that nebulae are going to tend to be teal or red, because when you ionize oxygen, you get a blue color, bluish teal color. And when you ionize hydrogen, you get this red color, like my shirt. Okay? So that's what we're seeing here. And if we back out, we'll show you the whole image at the moment just so you can see where it stands. And we are actually in a really, really beautiful area of the Cygnus Milky Way, where there's many, many stars. I'm going to color correct again. It's going to make it all stand out a little bit more. Look at that. Okay. Hey, Sheldon, how you doing? James Hyatt, what's up? And hey, and Marianne Robb is here. Yeah, Marianne, of course, is part of SkyTour Livestream. She is the one of the people that runs our organization. Tara Diulis is the other. And I am the third. I am the lowly worker. She tells me what to do, and I do it. Yeah, she makes demands, and I have to just say okay, because without her, none of this would have happened. And so that said, remember, like I said, if you get a chance, go to SkyTour Live and click donate. Help us get this new telescope into the new observatory. It's an even darker sky site than this one, believe it or not. This is a dark site, but that site where it could possibly be going to is even darker. So here is our all-sky camera right now. That's the moon at the current site. So that's the first quarter moon. Here's the Milky Way. See that? Even with the moon, we can see the Milky Way. It's beautiful. Okay, here's the Pleiades coming up. Orion just rising over here. There's Betelgeuse. Had Betelgeuse gone supernova already and showed up here on Earth, this would probably be as bright as the moon right here. This would be a gigantic blob over here, because Betelgeuse, not quite as bright, but Betelgeuse will be visible in the daytime sky when it goes off. All right, we'll see it in the daytime sky for several months possibly. That is incredible. That is incredible. That's what you get when you get a supernova. But look at the central veil here. Look at this. Rich colors abound in the universe. And I was telling the group today when I was giving my lecture that every single element in their bodies was made in the heart of a very, very hot star. They were made, the elements in their bodies, it makes them magnesium, potassium, salts, and sodium chloride, sodium and chlorine. Those were all made at millions of degrees Celsius in the heart of a star. And after being liberated to the interstellar medium, they cooled off. And once in the medium, when they cooled off, well then they got down near absolute zero, these little elements. And then there was also dust made by stars that are supernova, and by these red giants that slough off all this stuff, slough off their outer layers. And that dust can form molecules of material out there, and they will form dust grains. The dust grains are a very, very fine material, a micron in size, a millionth of a meter in size. Okay, and yes, just for you, Michael Hedrick, here is a inverse view And to see it like we look at it as astronomers, we actually will look at these in black and white like this. Okay, and by doing a push on this, we can actually get this detail to show up really, really solidly bright. Okay, so now we can see the detail very, very carefully. See all these wisps? Those are hard to see when we're looking at it like this. Okay, without the inverse. Okay, that's how it looks in black and white. You miss a lot of the detail, but when you look at this inverse in this way, now you can study these filaments in more detail. Look at this. Let's zoom in on this. Look at this filament. Look at the detail in this filament. You know, that's hard to see when you're looking at stars that are bright white and you know, causing the pupil of your eye to block, you know, to stop down a little bit. But you can see everything with more detail like this. And depending on how we do this, we could, in fact, make them even more visible. Okay, like this, increase the contrast. And with an inverse, we can actually get a pretty solid view of this material, you see. And there's a limit to what we can do. So you process it just enough. All right. So there is the central veil, and it shows us the extent of this wispiness. And if you're looking at it like this, it looks pretty good, right? Now, if we actually were to then just come out of this inverse view and then put in the color again, now you get more indications of what's really there. We wouldn't know what was hydrogen and what was the oxygen, all right? In this view, when we see the color, well, we can still break it out. It's just a slightly different color. Okay, the hydrogen is this teal color, and the oxygen is this dark color, which is interesting. Okay, but I prefer the color views when we're doing outreach stuff like this. It's just beautiful. So SkyTour fan question says, SkyTour Live fan question, what type of star would you be, what type of star would you be since we're all make of star? Re-ask that question. I'm not quite sure what you mean. Okay, let me, if you're asking what kind of stars would be responsible for making the elements in our body, massive stars, really massive stars. Now you might say, but wait, these massive stars, you know, they only live a few million years. That's correct. But the universe is 13.8 billion years old. So that means that over the time the universe has been here, many massive stars have come and gone, exploded in a supernova, scattered their guts to the universe, and that material has had time to scatter around the universe because it's happening everywhere. In all galaxies, it's happening. So there's a lot happening to promote star building and planet building. All right, and so we see a lot of this material, and it clumps in galaxies because galaxies also have supermassive black holes at their core. And so material will accrete around the black holes and circle it like stars circle the galaxy, ours do. And you know, we've been around the galaxy's center about 20 times since we were formed 4.6 billion years ago. So we've had quite a journey. Okay. All right, we are at 26 here, and we've got it set up. We're going to save it here. All right. And we'll save it exactly as seen. Okay. And now what we're going to do is we're going to move down and bring this up, and we're going to take and view the rest of this. And then we're going to come down here, and you can see it right here. But we're going to go into our low light mode. Let's go to 1 second and go into our low light mode. Okay, and let's label it again, and we're gonna bring this star up to about here, and then we'll have the bottom facing us. Okay, so we're gonna do that right now. Okay, we're moving ourselves south. I hope you like our labeling feature that we have in here. It's really cool. Okay, let's go up one more little chunk. Put that star just outside the view. Okay. All right, so now we have it set up so we can now look at the bottom of Pickering's triangle. And then we'll be able to make that one big image later. I'm actually go a little more because no, this is good. This is good. It's all going to be there. Okay. All right. So let's do another 25-second shot so we can show you the rest of the story, as Paul Harvey used to say. And now for the rest of the story. All right. Out of this mode, let's go back into our live stack. And you'll see the previous image that was in there possibly. It's in the buffer. All right. And there it is. This is the central veil at this point. And this is the bottom. And now this star that we have here is moved up to the top, just out of view. So we'll see the bottom of this all the way down here. So you can see more detail. Michael Hedrick has a question. Random question. Uh-oh, the worst kind. What was the size or count of the silver grains were you used to do old school? Oh, yeah. You're talking about silver halide. It depended on the film, Michael Hedrick, because one of the things I used to do was take photos on glass plates. Glass plates have been used since the 1800s, and the university where I got my astronomy degree had one of these 100-year-old refractors in there, basically a lens system, but it was a 20-inch diameter. That's called an Alvin Clark refractor. Alvin Clark. If you look it up, you'll see that, wow, that's actually really, really cool. And the Alvin Clark refractors are highly sought after if you can get them, because Alvin Clark was the best maker of these things. And as it turns out, the film grain that you use will determine how many of those crystals are in a square centimeter, say, of the plate. So it varied, okay? If you had 400 ASA film, that was considered a relatively fast film, not really compared to the digital cameras today, which can go to like 800,000 ISO, which is the speed setting. And we still use ISO ratings, and so those the density of the crystals depends on the film that you're using. So the really fine-grained stuff is an extremely dense layering of these crystals, so you get very, very fine resolution. Coarse resolution was faster to receive data, but we got a much better image because we saw it was coarsely sensitive to allow for a lot of sensitivity in a short amount of time. Okay, so now you see Pickering's triangle up there that we're looking at, and now the bottom of it is here. Okay. Yeah, and there's all kinds of other stuff out here as well. We're literally looking at the remains of a star that obliterated itself. And in the middle of all of this, let me go to Stellarium for a second. Okay, we bring up Stellarium. In the middle of all this right here, okay, that's the Crescent Nebula, we don't want to be there. In the middle of all this, we actually have something interesting, because right where this is, all right, let's just grab it. Okay, if we zoom in, we don't see a neutron star where this explosion took place. So it might be a black hole, and it's actually Cygnus X5. So look up Cygnus X5, and you'll find out some details. Because Daryl couldn't join us today, I would ask him to do it, but I'm doing 17 things at once, so it's hard to do all that at once. Then again, I might be able to do it. I just don't like doing it when you guys are like waiting for me to get to something. But we're waiting for this image to come in. So let me look up Cygnus X5 and give you an example. It's the center here. Cygnus X5 turns out to be a song as well. I just figured I'd throw that in there. Let's find out. It's a motorcycle. Go figure. Okay, I think I probably should kind of label it. All right. I'm looking for the data here. How are they labeling it? Okay. Okay, let's see. Okay, what it says here, you gotta understand it's, and as I said, it's probably a black hole. But I'll read to you about Cygnus X5. Cygnus X5 is likely not a neutron star or a pulsar. A pulsar is a type of neutron star that has a hot spot that flashes, as it rotates very fast. It's thought to be a black hole, and it's too large to be a neutron star, according to current stellar evolution models. Now, the key points about this is that because of its mass and invisibility, they think that it's actually a black hole. But we haven't found the source of Cygnus X5 yet. We haven't found the actual, or proven that it's actually the progenitor star for this particular nebula. So it's something we haven't done yet, but it is something that is on the docket to figure out, without a doubt. I have a feeling the James Webb is going to appear at Cygnus X5 before long and help us figure it out. Okay, we're going to save these. There's only 13 of them here, but this is fine for now. As it gets closer to the horizon, we're going to lose detail. So we'll stop here. This is the bottom half of the Pickering's triangle here, and I'll put those together for you later, and you'll see them all together. I'll send them out. I'll put them in Facebook or something. Okay. Now we'll come out of here, and we'll go back to our low light mode. I love this. Low light mode's a lot of fun because it's like having a finder that's like incredibly good at what it does. Okay, let me get rid of those lines. Okay, and bring us to better speed. Okay, now let's come back here to our stellarium. Zoom out a little bit. I'll show you how close we are to the horizon. Look at that. Okay, right now we are literally only 30 degrees above the horizon. And at 30 degrees above the horizon, things start to get fuzzy real fast, so we're going to avoid that. So we're going to swing around this side of the pole, and now we're going to do this. We're going to head up here, go into the dark a little bit, a little darker area. Okay, this is the W of Cassiopeia here. And I'm going to bring us here, because there's a really cool nebula here that I've taken a picture of before, and I'm going to take a picture of it with you now. And hopefully we won't have to refocus, but we may. Alright, so watch the telescope now. It's going to swing around. There it goes. It's always been cool when I think about it, because the telescope is literally swinging around 2,600 miles away from me. You know? So if anyone's out there, they're going, where's that thing come? How's that moving? You know? And that's what's happening. It's really just something else. Okay, that's the star Navi. It's good, we got it. Navi is in the constellation of Cassiopeia right here. All right. And so if we come in here and look at Navi, okay, This here is upside down, so we're gonna find it is going to be below Navi. So I'm gonna move it over to the west because we're looking back. It's actually to the side here. And we should see it when we get there. Now with the moon out, it's going to be a little trickier because the sky has some brightness to it. Let me go back here and make sure I'm doing this right because I want to... yeah, Kaz. It's going to be... Oh, duh. Sorry, the whole scene was... The telescope's upside down, so it's actually right here. Like I expected, and I was wondering why I was going down. Okay. Alright, so now we're going to go back toward the east. And Navi is a very, very hot star, and it's actually throwing off a lot of ultraviolet energy. And ultraviolet energy is responsible for ionizing hydrogen that's right here in this region of the sky. And you'll see, this is the main nebula here. You'll see another one up here. Okay, so we'll let this, let's bring that down just a little bit more. Okay, and then we'll just pop it east a little bit more, which means that everything's going to shift to the right a little bit. Okay, there we go. All right, and as far as the focus, let me zoom in and see how the stars look. It's hard to look at, right? Because we got all this digital noise in here. That noise can be reduced if we drop the gain here down. Okay. But then, of course, you see that. You don't see anything. So we want to be able to see stars in here. We want to see what we're doing. And we would do it. We wouldn't see all that noise. But if we don't go to these higher levels... Okay, I'm going to actually do this at 250 because that would be easier for us. Instead of 350, I'll do 250. All right. So now I do that. It's a little bit better. So focus seems okay. So I'll back out now. And there's Navi. All right. And so here's what we'll do now. We'll now do a 25-second shot like this. Off it goes, and we'll get out of the low light mode. Navi's there. We're gonna see a nebula right in here. Okay, and there's gonna be a lot of stars in here too, so you're gonna see a really interesting scene here. This is a region of the universe that's really hot. Okay, this is the previous shot, the lower part of the Pickering's triangle feature in the Veil supernova nebula remnant. So you see right here, you'll see it in just a second in this next exposure. Well, not like that, you won't. We gotta do this first. There we go. So there's Navi, and there is, this is actually called the Ghost Nebula, which is kind of funny. On Halloween we shot this because it's the Ghost Nebula. It was neat. So here we are. And we have two. We're going to ride that curve almost to the top to get maximum darkness without losing detail. Look at that. We have this blue over here. This is a reflection nebula. There's all dark dust in here. Navi's halo is due to our system being so fast photographically. It's a trade-off. You want to see this, or do you want the star to be perfect? I choose to see this. So look at this beautiful image, and color correct it a little bit. So as this develops a little more, you're going to end up seeing the beautiful wispy details in here, which will become clear very soon. And then you'll see that this stuff is actually quite complex. And this is a shelf of dark nebula in here through which the star's blue light is being scattered on this side of it. So the star can, see that this is too dense for the starlight to start doing anything like scatter for the dust particles to scatter the starlight, or it might be farther away. There's a lot of orientations we do not understand in the universe, and it's only implied when we see this. We have 5 here done so far. Let's zoom in a little. Now you can see some details, and now I can pull this mid-range in to kind of brighten up the nebulae. See that? Yeah. Again, we're not ready for the inverse of it yet. Right, but you can see some complexity developing in here. Okay. To those watching on the big screen, sorry about that bright white suddenly. Okay, let's go here. Get rid of that. So yeah, we can take away this guy here, pull him down, allowing you to see the full frame on the screen. Nice. Hello, Hein Cherry is with us, or Hein Shari. I'm not sure how you say your name. I'd love to know. Is it Chari or is it Shari or Shari? Okay. So again, looking at this developing, I have to say, this is relatively faint. So the fact that we can see it this well shows that it's really, the telescope is really performing well. It was hard to see the details in here with any previous attempts we did with the old camera. With the new camera and with the color settings the way they are, everything is just optimal now. You know what'd be cool? I'm wondering if there's a way that I can write a programmatical thing to remove the stars and just show the nebulas developing. I'll have to think about that. It might be a button you push or something to actually do that. That could be, so we'll see. Marianne's talking about Gilligan. Skipper. Not that Gilligan. Marianne was a cop, of course, and when she says her team, she means her police team. And I think Gilligan's a somewhat common name. Yeah, okay. Michael Hedrick here, retracting a lot of messages. Are you saying bad things? No. Okay. So we have, right now, we have got 13 images stacked here. We come in here, I'll show you. See the 13 right there. So this is 5 minutes and 25 seconds we've been exposing this. Now, typically this would take quite a lot of time, quite a lot longer time than that to do it, but because our telescope is really optimal and it's 25 times faster thanks to the hyperstar system from Starizona in Tucson, we we can do all of these things in a very short amount of time. Much better. Yeah. Or we use Star Exterminator from RC as well. Yeah, Daryl's fine, Cosmic. He asked if he's okay. Daryl's got a computer problem. So it's so slow that he can't join our streams without it bogging him down and probably us. So he's gonna get his computer fixed probably on Monday, I think he said. And so we'll be able to. I don't think there's fixing it. I mean, it's so old. It's probably just said I can't do it anymore. Just went, it was done. And that's probably what happened. But he's fine. I talked to him just before this just to find out if he wanted to come in. And he says, no, my computer is too slow. His dog's slow. So look at the development of the detail here. Zoom in on that. We'll zoom in on the ghost section of the nebula. Look at that. Okay. There we go. Kathy's with us. Hi, Kathy Pernisic. How are you? Wow. Yes, ex-lady, correct. You'll see. Okay, so the hydrogen gas is being illuminated here. Let me just show you. So here, this is hydrogen that's being ionized all along this front. Okay. However, there's dust in here as well, and the dust is showing a subtle scattering effect because it's taking the blue light from Navi down there. Okay, down there, a really bright star that we know is down in the lower right, and it's actually scattering some of that blue light, which gives it this look. But because the hydrogen is denser along this front, okay, because of that, the hydrogen gas dominates the brightness and the color, so the hydrogen shows up more. Where the dark nebula is brighter, or more dense rather, it means that it's going to also be brighter. Okay, so for instance, up there, okay, as we move up, okay, this region up here, all right. Let's get up there. Okay, this region right here. Okay, this region is filled with very dense dust, and so any hydrogen that's ionized in here has to play second fiddle. See, there's a little subtle line there. Well, you see, this is dominant here. There's a lot of hydrogen here, a lot of hydrogen here, less so here. It doesn't, the universe doesn't have to have a layout in any particular way. It doesn't need to have a certain amount. It can have literally a variety of different amounts, and that's how that works, and that's exactly what we see in these nebulae. Okay, let's do this now. All right. Okay, so we are looking at this nebula. Check it out now. This nebula is really looking pretty. And there's Navi down there. By the way, the star, you'll notice that this is the point here, and you see it trailing off this way in this. There's no mystery to why this arrow is pointing right to the star. It's because this part of the star, this part of the nebula is very dense. So the starlight, the very, very powerful stellar wind, is pushing material back, okay, this way and there, but this part is strong. It's very, very much higher density, and resistant to what we call stellar erosion by the high radiation content spewing at it. So we're getting something shaped toward the star. We see this all over the place. All over the place. It happens everywhere. Okay? And that's what we see. Waldo hiding. Are you admitting something? Marianne, I think you have an admirer. Daryl will be back when his computer is fixed. Look at that, though. Look at that beautiful richness. That's really looking good. Let's bring this back for a minute. There we go. Bring this up. All right, Marianne's going to be heading down to our new site. You know, hope you guys can help us out. Again, go to skytourlive.org here, and if you want to donate, boy, oh boy, that'll really help us out. We got to get the money to put that thing in there. I don't want to lose this opportunity because it's a perfect opportunity to be on a mountain with other astronomers, and the price is literally half of what it would cost. Literally half of what it would cost if we weren't a non-profit organization. So if you could, give us a Christmas gift. And it's all a write-off, by the way. It's all a write-off. It's all something you can write off. Okay, Marianne. Let's see. What am I looking at? We got more questions. All right. There is a question in chat you might be interested. Okay, let me look for it. There we are. Where is it? Oh, you new theory. Stars are the reasons for most or all everything in the universe. Could be a starless universe. Could a starless universe never exist? Well, that's actually quite a good philosophical question. That goes into cosmology. But I will say, thank you, C&D boy. I will say that stars are a natural occurrence in a galaxy where there's mostly hydrogen. Hydrogen is the most simple element there is. It starts with one elementary particle called a proton and one elementary particle called the electron. Okay? And electrons are particles called leptons. And when we look at the proton and the electrons interaction, the electron is a -1 charge, the proton's a +1 charge. And that happens, the way these particles were built is the most important thing to understand. The electron is the most fundamental particle. There's no particle within it that makes it up. It is the smallest from what we know now. The proton, on the other hand, is made of these things called quarks. Quarks, quarks. And in the case of the quarks, the quarks have this fractional charge. And there's 3 quarks that make up a proton. Okay? So a proton has these 2 up quarks and 1 down quark. And that's an up quark is 2/3 of a charge. Okay? And so that makes 4/3. And then we have, let's see, what did I get? It's made of 3 quarks. So +1 would actually be, how come? Mental block. I am so sorry. I'll get it right. Just a minute. But see, the neutron is the other one. The neutron has 0 charge. Okay, and again, it's made of 3 quarks. But what happens is, the up and down quarks make up the neutrons and makes up the protons. And the neutrons, if they end up in the nucleus of an atom, then there are processes by which one of the quarks in the neutron can be changed from down to an up quark. And when that happens, the neutron becomes a proton. And that's the reason you're here. And that's something that is managed by the weak force in nuclear physics. We have the strong force, the weak force, electromagnetic, which is light, and gravity. So the strong force holds the nuclei together. Okay, you can pack in a lot of +1 charged protons, like the north poles of all these magnets shoved together. It's not magnetism, but you know how hard it is to push 2 magnets together, and like that, they're north poles. And so that leads to the need for a strong force to bind the nucleus together, and that's what happens. And part of that is because the proton is made of these three quarks, and these three quarks are very, very powerful. They are held together to each other by a particle called the gluon, and the gluon is because they're so powerful together, there's a residual force that reaches outside of that proton by a certain amount of distance, very, very tiny amount. So there's a residual force outside of each proton that helps bind another proton in with it, and they just, each one has this residual force, and you can get a nucleus that's about 118 protons in count, and that's the maximum that you can get. Beyond that, you can have a 119 or a 120, 122, but they decay back immediately to something that's 118. Okay, which is agonescent, which is one of the it's above 115 by 3. Okay, so it's pretty cool. So we'll let this go a few more. We're going to let it go to a couple more, and then we will save it. I'm actually going to look at this here, go to the end of this, see where we are. Okay, let's now do this. I haven't saved it yet. I was running it, so we might have a little error message. That's what we want. Gamma cast nebula. Set the target name. Are you going to complain? Save it with the annotations. Good. All right, no complaint. Good. So then we come out and we save the full field. We're gonna save this. We don't save this close up. That's just a visual thing while we're doing this. So we can save it now as this, and save it exactly as seen, like this. Okay. So the Gamma Cast Nebula is really pretty and is incredible. Michael Galea, I just made a donation to SkyTour Live. You're the man. Thank you so much, man. That is so cool. You know, I'm looking forward to being able to do this. We, you know, as I said, I'm not asking you to pay me anything. You're actually helping to further the science, and to be on a mountain with astronomers, professional astronomers, means that we'll be surrounded by people that are like me, and that won't that won't take any equipment for granted, and there won't be any problems. We'll have good coverage. We'll have people there watching stuff. It's going to be perfect. So I'm looking forward to that. But thank you, Michael. Thank you so much. Wow. Okay. One more save here, and then we'll come out and I'll show you a really beautiful jewel box. Yes, there are jewel boxes in the universe. I will show you one now. Okay. So we go to 1 second. This is our low light mode, and we can't even get a hint that this nebula is here, and that's because it is very faint. And even though it's faint, we can actually see it when we do our time exposure. Yeah, one of these days I'm going to have to take you through the entire thought process and evolution of SkyTour, SkyTour live stream, to show you how it first started, how it went from being out in the front yard here in Connecticut to being out in the desert in Arizona, how we went from the telescope, which is behind me right now, to this telescope that's up there now, and then to move on from there to figure out how we went from a magnified field view to a very wide field view, and how the cameras and changing of the cameras led to an optimal view of with our telescope. That's a story in itself. It could be a little documentary almost, but you know, this observatory you're seeing above me right there, started as a yellow plastic flag in the middle of the desert, on the desert floor, and then that became a square concrete platform some months later, and then that became a building on that square concrete platform. But the day it was poured, I was on it in night, actually photographing the sky, okay, from it. Let me come back here. Okay, so there's the moon. It's on its way to setting. Here's the Pleiades. Orion is up higher now. These are just glares from the moon. Okay. All right. So let's go look at let's zoom out of this a little bit, because this will be nice. We'll come over here, and we're going to go to this beautiful jewel box. This jewel box is among one of the nicest clusters in the sky. I'll tell you about it in just a minute. Okay, let's see here. 1 second, please. There it is. Okay, so I will move up and over. There we go. Okay, move it over. So these clusters are interesting. Now, it's called a double cluster, and you might assume that they're right next to each other. Well, they're not. If you look carefully, you'll notice this cluster is bigger than this one. So they're actually like this. One is way up here and one is back here. But they're together in the sky, and so it looks like they're right next to each other, but they're not. They're separated by a number of light years between each other. One is further away than the other. The further away one looks more compact. Okay? Now, when we look at this, we don't really see any color in here at this point, but the stars are definitely in color, and we're going to check those out in just a minute. I'm going to move over here. I'm going to move west a little bit, center it up. You can start to see as they move that one of these is red. You can see that red star right there. There are some red giants in here, so the cluster has evolved and managed to stay cohesive. Okay. All right. So let's do this. Let's do a 20-second shot here. That's all we're going to need for this. All right. And we'll get out of our low light mode and go into our beautiful deep sky mode. See these beautiful jewels. And in deep sky mode, you'll see the Gamma Nebula. Gamma Cassiopeia is Navi, this star. And that'll go away in just a second, and we'll see the beautiful double cluster. And so you'll see it momentarily. Oh yeah, look at that. Oh, it's beautiful. That is a really pretty double cluster. Now let's color correct, and let's do some processing to kind of give it a more of a proper look. There we go. See, now that shows us the beautiful red stars in here that are the red giants in this cluster. Let's go back up our curve a little, not quite all the way. Get a little darker sky. Look at that. We'll let that develop for a few minutes. It's like developing film almost back in the day. Okay. All right, let's let this do this for just a minute or two. JSCO says Mordor asked me a question. Let me go look what he said. Let's see. Mordor says, may I send Daryl a PC? I have a tiny PC that is pretty new, not doing much. Well, Daryl, if you're listening right now, what do you say to that? You know, that's a very, very nice offer from Mordor. You know, let me go see if I can get him. He gets frustrated, you know, because he can't. You know, he can't basically get in. It frustrates him, you know. Let me see if he'll. Hey, Daryl, let's find out here. Is it one of those mini computers? Like, what should I tell him? Waldo says, Mark, you come a long way. I've been tuning in for many years. That's funny. Thank you. That's very kind. There was a guy I met today, Colin, in our at the talk, and he's a brand new field investigator from MUFON, and he said that he's been following us too for a long time, and that he's really excited to do more of it. And I think, wow, that's just very cool. I mean, there's no place else to get this. There's nobody doing this out there, you know. And he hasn't written back yet, by the way, on the computer thing. But Mordor, that's a really, really nice offer, and let's see if we can get him to respond to that. SkyTour Live fan is heading to bed. Good night. That's Evan, I believe. Good night, Evan. You know, very cool. Yeah, so we zoom in now. We can see this a little more detail. These red stars are in the cluster, okay? They're in this cluster, the larger cluster, the one closer to us. They are red giant stars. They have used up all their hydrogen fuel, and their core began to contract, which causes that the outward flow of pressure, you know, radiation pressure to increase, and solar wind to increase. It pushes the outer envelope out and makes the star balloon upwards. And as it balloons upward and away from the core, which is hot, the outer gas is cooler because it's further from the place where the fusion is taking place. And that means it's going to get redder. So I think that's pretty cool. And that redder color is what we see in these red giants. These are very large stars. Okay. And we have Bodacious. How you doing, Bo? Nice to see you. And he says, are entangled particles really black holes? That is an extremely dense question, no pun intended. But we have a problem understanding what's going on inside black holes. Everything is theoretical. But it's actually collapsed stars, technically, are the black holes. And what the particles moving into them do beyond that is just something that we don't understand yet quite. We have some ideas what's going on inside a black hole. We know what happens when you approach a black hole, when you approach that place that we can see all the way up to, called the event horizon. And beyond that, we can't really see very much. And we can't see anything. So it's all theoretical what's going on in there. So I don't know if there's an entanglement process that begins after passing the event horizon or not. There might be, you know. Now let me explain what entanglement is, okay? Because we hear quantum entanglement all the time. And yeah, I'll answer that question in a minute too about mini black holes. In fact, my lecture today was about micro black holes, along with other particles that CERN did create. And so the problem is that when you have particles that are entangled, we usually apply them to atomic particles. For instance, there are many characteristics of atomic particles. Let's take the electron. Electrons have a spin property. They can be spin up or spin down. Okay. Now the way entanglement works, and it's interesting that it works this way at all, is that if you have a piece of material, and let's say you separate it and put one half in a laboratory 1,000 miles away, and the other half in a laboratory 1,000 miles away further, so they're 2,000 miles apart, and you measure the spin property of the electrons in the material here, and you measure them, they spin up. You don't have to measure the ones over here, 2,000 miles away. You'll know that they are, in fact, spin down. They are. It's like a conservation type process going on, it seems. And if you change the property of the spin up electrons to spin down, let's say you can do that, then the spin down electrons here will necessarily make the electrons over here spin up. And that can happen over light years of distance. What is it saying? It's saying that there's some type of entanglement, that the particles have information. They know what the other particles are doing no matter how far away they are. That's why Einstein called this spooky action at a distance. And it really is spooky action at a distance, because it really is something that is the most unknown quantity there is. We don't know how quantum entanglement really works. Oh yeah, we can calculate it. We can say what will be entangled or not. But Bodacious says maybe some type of unknown fluid. Well, let's look at water, for instance. Water is essentially non-compressible. So if you were to push on one side of the water, instantly the other end would also bow out, because it's not compressible effectively. There is a tiny bit of compressibility. But so that's sort of an instant transfer. So it's some type of universe fluid type dynamic, maybe. Something we don't yet fully understand. We do know that when black holes merge, they cause ripples in the fabric of space that we can see as gravitational waves. But waves ripple through a medium. What is that medium? The space fabric. What is the space fabric? The time, the space, the continuum, which is X, Y, and Z moving through time. It is all of that stuff, and there's a ripple. It's a physical fabric of space. That's the quote-unquote fluid that we're talking about here. So we have to be careful of what we use for terminology, because it doesn't act like a fluid we know. Okay, it doesn't act like anything that we understand, except in the context of the fabric of space construct. Yet, quantum entanglement works across all distance. And that's the thing that's really fascinating. There is a connection, and thinking of it as a fluid bow is actually not a bad way to think about it, because we know that fluids aren't compressible, okay, effectively. And then he says, well, entanglement. Some say it's done by consciousness. Yes, that's true. There are some people that say that. However, when they measure the entangled electrons, for instance, they look at the spin up and spin down property. They're not changing it, because the electrons, if you measure them, they're spin up. You didn't make them spin up. Okay, that was what they were, and therefore the other ones are already spin down. You didn't make that happen. They were already spin down. You just measured it. But the thing is, the idea is you don't even have to measure the other ones. If these are spin up, you know these are going to be spin down. And if you change these to spin down through some mechanism, then you know that these are going to turn to spin up. And so it's like there is a string connecting everything together, you know. And so that's for cosmologists to puzzle out. But it's really quite an amazing, unbelievable thought process, you know. Let's identify this, and we'll see the identification here. The two clusters, we'll save it with annotations. All right, excellent. So now on the server, okay, let me also pick one. We'll call it Kai Persi, and we'll set that target name. Okay, and then we'll come out of this and show you the annotated image. This is what you'll get. You see the annotation? There's faint red circles around this. Okay, so you can actually see what you're looking at. That's up on the server as well, probably there already. And then we will save this, and it'll save in an astronomical fits format, which allows you to do all the processing if you want. But then I give you the ping file, so you can actually just download a pretty picture and not have to do any work at all. Yeah, Bo says the thought is it doesn't know what it wants to be until it's observed. There is a concept that says that does it have any measurement at all until we actually measure it? Does it have any entanglement, or does it have spin until we measure, or unless we measure it, or does it even exist until we measure it? Yeah. Philosophically, with the way the universe works, I would say that it's a property that's there, and we just don't know what it is until we measure it. Kind of interesting. Here's Astro Ape. Hey, Astro, how you doing, man? He says, just stumbled upon the channel. Cool stream, thanks. I'm currently inside warming up from doing some visual observing with a 5-inch refractor. Mainly just doing some planetaries since Jupiter's at opposition. Yeah, that's right. Jupiter's in the best possible view. And I've been waiting as the evening rolls by to see if we can get a look at Jupiter. And let's go take a look in our stellarium. You guys, if you haven't seen us before or joined us before, stick around, hang out. You know, become part of the SkyTour group. It's all free. We don't charge anything. I'm a professional astronomer. That's what I do for a living. And so I do a public outreach with my astronomy here. And I would very much enjoy having more people join us. You know, we do this on clear nights, and we make everything we take available to you. This image here, the double cluster, that'll be here on skytourlive.org. You go up there, scroll down, it says take me to cool pictures, and you can go there. We're developing an app that will be available too, where we can actually let you, for instance, search for all times you've ever taken pictures of this, look at all the images of what we've taken in one complete location. It's just gorgeous. It's a beautiful app, courtesy of Izabela Melamed in Bulgaria, who developed it for us using our data. All right, Jupiter is at what altitude right now? Plus 49. We might be able to see it. Let me just back out a little bit. It's going to be like this, so we might be able to see it. We have a wall. That's this wall here, toward the east, where the telescope is right here, looking right now somewhat toward the north. So this wall ends up right around here, maybe here, and it's close. We can see the North Star without any problem, but then we have this wall to contend with here. So the North Star is just above the wall here. Then we have this wall here, but I think we can see it. You'll find I'm going to show you Jupiter tonight too, because Jupiter, being in opposition, we may have the best view of it, but you have to understand that we have a wide field system here. We do not have a planetary type scope, but I'll do it anyway. But just remember, these are the kind of views that we do well, right? And I just save this. That's out there. I'll save it one more time. Okay. Save our fits file. Then we'll save it exactly as seen. Here we are. Okay. And let's go see if we can see anything on Jupiter's in Jupiter's cloud bands. It may, or bands and zones. Not sure. We'll see, but we're gonna try. We will try. Bo asked another question. The Great Attractor, is it the very start of the Big Bang still flying through? No. Still flying through space. No. The Great Attractor is where everything seems to be going towards. Okay. The Big Bang was an outflow process, not an inflow. We just look like we're heading towards some spot in space. And as far as we know, we don't feel that the Big Bang is... we don't feel that the Big Bang is something that we can just look in a direction and see it. Because it kind of happened everywhere. This is one of those things that now is tough to follow. I grant you. Let me get my camera back here. Hi guys, I'm here. All right. So let's now go over to Jupiter, and we'll zoom in on it here. And you'll be able to you watch the telescope, and you'll see the telescope moving. And if it intersects this wall, we won't be able to. It won't hit it, but we won't see Jupiter too well. But let's go check it out anyway. All right. We're gonna go there. And away it goes, heading toward the eastern wall. I think it's high enough. Let me we're at 1 second. Let's do this. Oh yeah, we'll see Jupiter. Let me pull this out a little bit. Okay, Jupiter is just up there. So we're going to head up north. Jupiter's going to be bright in our telescope. I'll drop down the values so that we can actually see it. You're going to see multiple rings, like these halos, because of our system. Right? Nice thing is we'll see all the moons of Jupiter. And since we have this beautiful ability to autofocus, we'll be able to focus. This is an artifact of the bright object in the view here. Okay. So now what we do is we're going to drop this way down. So I'm going to go down to, let's say, 50 milliseconds. All right. And it does that. And now I'm going to drop out this right here. And I'm also going to drop down the sensitivity on the sensor. Okay, you notice that our moons disappeared, but Jupiter is still overexposed. So, let's see if we can get any kind of view of the cloud bands at this point. Oh yeah, look at that. There they are. Yeah, let's pull it back up a little. Okay, pull it up a little more. Okay, for us to see the cloud bands on Jupiter, we have to necessarily eliminate seeing the moons of Jupiter. Okay. So you can see we see the two major bands right there. Again, we're not a planetary telescope. We are a nebula telescope. So the fact that we can see this is actually pretty cool. But the new telescope we want to put in the Benson, Arizona at 3,600 feet is going to... I'll show you how big Jupiter is going to be in that, just natively. Jupiter will be about this big natively in that telescope. And it's going to be extremely sharp and clear. We'll see all these bands plus many more. We'll be able to count many bands on Jupiter with that telescope. Yeah, let's see here. Let's go zoom in a little more. Okay, we're zoomed into 317% of our sensor. You can see the color really well. You see the limb darkening very well on Jupiter. Yeah. Again, this, like I said, not a planetary telescope. The one that we're putting in Benson will be, and we'll be able to do a lot more with it. We'll be able to look at, actually, we'll be able to look at Jupiter and get an idea of what its atmosphere is composed of, because we're going to have a spectroscopic system built into this one, because it's already in there. I have that component here, and it already works beautifully. Okay. So, what I'll do, I might as well, I'll just take a snapshot and see how that works. Let's see what it looks like. It's gonna be a little tiny thing. We'll zoom in. So you see a single snapshot. Obviously, we have an artifact in there that will go away when we're done with it. But it's pretty cool. Thanks, Astro Ape. The GRS is the Great Red Spot. Yep. We can see these upper areas. See, these guys here are a dark region up here. Then we see these light zones here, these darker bands. All right, and then more. And Jupiter, as it climbs higher in the sky, it'll be better and better and better. But you're starting to see more than just the two bands now. Okay, and that's pretty cool. Well, with the new telescope, we will be able to see this way better. Way better. Sheldon Harrison says, unfortunately, it's cloudy in Ontario, but this is great. It beats my 6-inch mirror. You know, for planets, you don't really need a big mirror, though. That's the thing, you know. So it doesn't necessarily beat your 6-inch mirror. This telescope is overkill for this planet right now, because we've got this low light, this very what am I saying? We have this wide field system on here, and that wide field system is enough to basically make it so Jupiter is just incredibly small in our field of view. But we still see some stuff in there. That's pretty cool. We can start to see details in the cloud bands down here. That's nice. That's actually the nicest that Jupiter has ever appeared in our telescope. But then again, this is the first time I'm photographing it with this new camera. The old camera would never have shown it like this. Alright? This camera is tuned to the telescope perfectly. We're getting the perfect arc second per pixel count with this particular camera that's on here. And the camera we're using is the ZWO 183 MC Pro. So that means color camera pro, obviously. You can see the color of the bands right there. Color of the belts, I mean. Belts and zones. Very interesting. Interesting thing about Jupiter, we just think that there's a white stripe and a brown stripe, but you know what's really going on there? The white stripes, all right, and the brown stripes are at two different altitudes in the atmosphere, all right? One is really high up and drops off into the other, all right? And the brown color is due to a tiny percentage of an impurity in the hydrogen atmosphere of Jupiter. Just a single tiny impurity is making that color and all the colors we see in Jupiter. At the poles, the Juno probe, which is circling Jupiter as we speak right now, you know, the probe has these swirly patterns of blue. It shows those very well. And that color, again, is due to impurities. And there's an ammonia compound that causes the beautiful red color we see here. And the hydrogen, the base hydrogen atmosphere of Jupiter means that had it acquired more mass, it could have been a star. But Jupiter is not a failed star. Jupiter is a planet that could never have become a star. unless it originally had acquired a lot more mass. Jupiter needs about 80 times the mass it has right now in order to be able to, be a star. And right now, it doesn't have that possibility. Okay? So that's pretty crazy. All right. 1 second here. I'm going to have to... There we go. We are... We're in a lull of Starlink where we don't have Starlink right now. There we go. Okay, it's back. Okay. So, every now and then Starlink is our service. Or we have Starlink out there. We used to have HughesNet, which is very, very slow. Now we use Starlink, which is like 30 times, 20 times faster. But if satellites are just not quite lined up, we'll lose service for a few seconds, which just happened. So everything froze up for a minute, and now it's back. Just have to wait it out. Okay, so Bodacious says he's in Anchorage, Alaska. Okay, that's a beautiful country up there. My uncle lived there for 5 years in the military in Anchorage. And my niece ran the Iditarod dog sled race up there. She has her own dog team, and she did the one of the legs of the run. And she was working with the team of Ramy Reddington, which is interesting, because Reddington's also the name of the guy in the Blacklist. So we're getting some good detail there, and you see that it comes and goes. Well, let me see if I can get us more detail. That's pretty cool. How about better quality? Does that help? You can even see now some variations in the cloud band. It's looking better. I think as Jupiter rises, we see a little more detail. And just because Jupiter's in a good spot to view tonight doesn't mean it's going to go away tomorrow. It's going to end up staying this way for months, so we'll be able to see it quite nicely. And with the new telescope that hopefully we can get installed in February, with your help, we will be able to see this way more detailed. Now let's do one thing. Let's capture. Let's take another snapshot. Okay. And it's going to the wrong location. It's going to the double cluster directory. I will move that. It might be going to a snapshot directory separately, but it looks like it's going to the Chi-Pergi cluster directory. But it will change. I don't think this knows where the planets are. Yeah. Doesn't. Okay, that's fine. I didn't think so. Alright, no worries. Anyway, let's increase our sensitivity of the sensor. We're going to lose the bands, and we're going to bring in the moons. Alright, so let's increase also the exposure. Let's set the exposure to, let's say 0.5. It'll be very bright. And then we'll have to no, that's 0.5 milliseconds. Huh? That was my mistake. Don't want it to be that. Well, let's actually try something while we're here. Yeah, okay, too bright. So let's go and do this. Let's back out. All right, because we're gonna look at the moons now. And let's go to 0.8 seconds. All right, and then we'll see the moons showing up. Okay, let's maximize. See that? That's the glare from our system. So let's pop that back out. And now we have 4 Galilean satellites. That's these guys. 1, 2, 3, 4. So let's go find out what those are. Because if we go in to Stellarium, and I know some folks in the chat already know, but if we come into Stellarium here, and we zoom in on Jupiter, okay, we can see by zooming in that we have, let's see here, we got one more out here. Like this. Grabby, grabby. There we go. Alright, so we have 1, 2, 3, 4 Galilean satellites. Now, we come in here, we zoom in, we see Io is out there, and it will look a little orange. And I'll show you that in a minute. But right now, Stellarium is only showing us 3 of the moons. Usually Stellarium is pretty much on the money. So let's see if maybe the time got shifted on us. Oh, interesting. So, in all likelihood, this is going to be Io here. Let me zoom in, because we can actually see the orange color of Io. If I actually drop this down to where the moons are less conspicuous, you can actually see the colors, and you can actually detect that color difference of Io. It's pretty cool. There we go. Now we're dropping those down. Let's zoom in. Oops, I went too far, didn't I? Hi, Judy M. John Proctor, hey, how you doing, man? How you been, John? I haven't talked to you for a long time. Hope all is going well for you. There's the 4th right there. Out there. Thank you, John. Yeah, I just was not... Oh, that's the 4th here, yes. But in Stellarium, I think we have to look at this. Okay. And... let me zoom out. There it is. You're right. Callisto. Thank you, John. That's right. That's Callisto. Alright, so we have Io, which is right here. Let me go back here. This looks like it's Io, and that looks like Callisto. Let me come back here now. Okay, Io and Callisto. And then the 2 close moons. This is Europa. We're sending a probe to Europa right now. It's on its way. And then we have Ganymede. This is the largest moon in the whole solar system. It's bigger than the planet Mercury. Pretty cool. So if this is Io, what you'll notice if we zoom in on it a little bit, okay, and it's going to be kind of hard to tell, but you'll notice it tends to be kind of orangey. And let me drop this exposure down a little bit more so you can see what the color looks like. Let me just increase it a couple notches. But you can see it's definitely orange compared to the others. And if we go, say, to Callisto, right, and look at Callisto out here, Callisto is going to be pretty bright relative to it because it's larger. But let's increase this brightness or the exposure. Now, what's happening too is you might say, well, wait a minute, Io is so much smaller Why is it brighter than Callisto? Because you got to remember, this is a big circular orbit. So Callisto may be far down in its orbit, and Io might be closer to us than Callisto, so it's going to look brighter. And Callisto is much bigger, you know? So there we go. There's the Galilean satellites. All these worlds are yours except Europa. Attempt no landing there. Use them together. Use them in peace. Yep. That was in the movie as well. The year we make contact, right? I think. All right. Okay. Well, this is a good place to end, I think, for tonight. With Jupiter, let's do one more view of Jupiter. Let's drop this down. Excuse me, and go to 0 gain. After all the talking I did today, my voice is pretty much shot. Okay, let's go here. Zoom in on it. Okay, and let's increase the brightness a little bit. That's going to probably be too much, but we'll find out. Nope, not too much. Not bad. Very, very good. So yeah, so we got our bands and zones, and we have the northern hemisphere of Jupiter right there. Looks really good. Cool. Well, guys, I think that's a good way to end. My voice is kind of shot from speaking for hours today. I'm glad you guys enjoyed. Those of you that just joined us, please take the time to subscribe. It's free, you know. And if you go to skytourlive.org, you can get all the photos we took tonight. I'll do one more right here. And they're free of charge. If you want to join our Patreon, then our Patreon will afford you the ability to get at the somewhat higher levels. You can actually get 4 images for the lower level Patreons per month, and at the higher level Patreons, you get all of our images throughout time that we've done as highly processed finished images. Now, if you also, and if you're thinking about Christmas, well, you haven't thought about Christmas unless you actually went to our, unless you've gone to our store. I have a feeling you'll love to see the types of things we've done in our store. We've got an incredible amount of products up there that are all available for you. And I don't know why the SkyTour or SkyTour shop is not listed up there. It should be. Yeah, okay, see, well, here it comes right there. So there it is, right here up in the upper right corner. On Etsy, go look for SkyTour shop, and then pick stores that are labeled SkyTour shop. And you'll get to all 45 or so of our products. We've got socks, we've got bathing suits, we've got boxer shorts, we've got water bottles of all kinds, we've got journals, notebooks, basically, that have a front and back with beautiful starry images on it. We have mouse pads, not that people use them that much anymore, but we have, clothing, we have all kinds of things. Lamps. The lamps are gorgeous with lampshades that are just stunning. And one of our lamps has the Flaming Star Nebula on it, which we just did the other night. And when you look at it, the lamp lights up the shade, and you see the flaming star, but it's reddish, and so your whole room has this red glow, kind of like me right now with my red lights that I use here in our stream. So I would entreat you to check out SkyTour shop, and also, think about donating to us. It's beautiful, and so thankful to the guys and the folks that have actually this time around. It's astronomy for all. and we actually love what we do. So I would hope that you would join us in our mission to try and bring astronomy to the world. Right now, we have a very good track record. It's getting better and better because Jupiter's getting higher in the sky. See that? So that's really pretty. But you know what? I can't really talk anymore. My voice is having trouble from talking so much. So you guys, you have a good night. And I will be back at you. And thank you for helping us get that observatory in place out in Benson. And getting the telescope in place out there. We have to get the pier. The pier is going to cost us a lot of money. And we're going to have the pier mounting the telescope way up high. But there is a way to allow us to be in a building that has a high wall line and be able to peer over those wall lines and see the horizons. And that's what we're doing in Benson. We couldn't do it here, but that's just because we have a mount on the telescope that's a fork mount here. We're going to transfer and convert this over to a German equatorial, as the current telescope, the new Celestron 11 that we have, is a German equatorial. And it'll be able to, once it comes active, it'll be able to look over the edges of the wall and have a much better view than this type of telescope mount will afford it. So, you guys have a good night. I look forward to seeing you on the next stream. One more time, here is our evening sky tonight. Right there, the moon is setting. Orion's coming up. It's nowhere near high enough right now. Here's Jupiter. Okay, Jupiter is the limit right now for us. The wall of the building is right about here. Alright, so we can't look below at Orion for several more hours right now. And so we have to wait a little while. But Orion's coming around, trust me. And when you see it, I'm going to promise you this because it's beautiful. When we look at Orion with this telescope, you're not just going to see the Orion Nebula. You're going to see the Orion Nebula. You're going to see dust and debris from countless supernova previous. You're going to see many different colors beyond the reds and the teals that we show. You're going to see beautiful cobalt blues. You're going to see greens. You're going to see other colors that happens still that you can see happening from the ionization of the different gases. You'll see the scattering nebulae, these blue nebulae that are made by dust grains that are scattering starlight. And you're going to find that the Orion location is just a veritable incubator for stars and planets. So you'll enjoy that. In just a couple more weeks, we'll be able to start looking at Orion. So you guys have a good night, and we will talk to you. And on the next time around, it's really getting better. See how it comes and goes? Sometimes we have, it's called fortuitous seeing. And we actually get really good sharp images, like right there. Okay, let me see if I can grab a snapshot of that. Might be too late. So you can actually, I can actually just record a short video. I'll record 20 seconds of Jupiter. And when I record 20 seconds of Jupiter, okay, now we're, yep, see, I'm getting the message again that we're not hooked up with Starlink. So we gotta wait a moment. It'll be back in a bit. So what we'll do is we'll actually get a 20-second shot here, all right, and that will allow us to then take that 20 seconds of video and stack them all together to make a better image. And I can do that. There we go. All right, so let's do a capture. Let's go here and do 20 seconds. All right. So we have a capture started for 20 seconds. and it's actually capturing our frames right now. So it's got 6 frames, 7 frames, 8 frames. All right. Meanwhile, I'll bring this back, because what happens when the connection restarts is sometimes we get repositioned, and I like to change it back. See, I was gonna go, and now we're doing one more thing. So that's me. I'm also known as just one more D'Antonio, and that's what I do. Okay. Okay. So we'll be able to stack these after. All right. So we did it. We got a number of frames that we got. So we'll be able to do that. Excellent. All right, guys. Now I really mean it. Now we're going to go. And I will see what I can do afterwards. Thanks, JSEO. Love you too, guys. All right. You have a good night. I'm gonna go and hit the hay. I have to be up early tomorrow. Of course, it's always the case. Oh, and little news. Progress is being made on our solar telescope observatory. I've got a solar telescope to my left in a closet waiting for a home, and we're gonna put it out in the front yard here in Connecticut. So I used to have a big dome on the front lawn. Now I'm gonna have a small enclosure that's remotely operated from here, and it will open and close the telescope and allow us to observe the sun all day. So we will actually have a all-day stream of the sun, looking at prominences and sunspots, and then from that we can actually make movies of the prominences coming off the sun, because they take hours to move, because sometimes they're as big as the Earth or even bigger. So we'll have that too, and that's going to be up and running as well. We're going to get Benson going too in February, hopefully. All right. So with your help, thanks, guys. Have a good night, and we will talk soon. And I really mean it now. Now I gotta really go. So good night, and you guys have a pleasant tomorrow. We'll see you soon. Bye bye.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming light for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light.